Okay, I'm going to briefly introduce about my research that is related to the ammonia fuel sulfate precursor for the MOS2 coating on porous metal surface to enhance its surface mechanical property. So MOS2 has been widely used in different industries such as automotive or machinery. And and mostly it is used as a lubricant. And the reason why it can be used as a lubricant is because of its a weak bonding force between layers. And this weak van der force bonding is allowed to make each layer slide between each other easily. And also the dry MS2 has the much lower friction coefficient than that of the wet MS2. So we can compare with the different fabrication approaches of the MS2 layer. What we use here is the hot injection method. It produces a very controllable process and the good properties, and the fabrication time is efficient. Okay. Also, the the annealing temperature is relatively low compared with others such as CVD or thermal decomposition. So what we use is right here is the hot injection method. So there are two main processes of my research. The first is the anodizing of aluminum alloy, and the second one is MOS2 coating. So we can see after anodizing aluminum alloy, uh, the nanopore form, and whose diameter is about 20 nanometer. And we fabricate this MOS2 liquid precursor by synthesis MO source that we use MO3 and ammonia as the precursor, homogenizing in 30 minutes with OLA. And for the sulfur source that we use, the sulfur powder homogenizing with OLA in 20 minutes. And then these two sources are injected into the three next flasks. Okay. So after this MOS2 precursor form, because it's a liquid phase, right? So it can be easily by sprayed or airbrush on any porous metal. Okay, on any porous metal, you can just simply coat it with no cost. Therefore, the multi-layer structure form. So we have basically we have three layers. First is the substrate, aluminum alloy substrate, and the AAO nanopore, and the MOS2 film. Okay. So we can see the SEM picture compare before and after coating. So before coating, there's a nanopore right here. After coating, the nanopore are sealed. And then we do the SEM EDS to estimate the weight ratio between MO and S, which is close to 1 to 2. For the quantitative precise measurement, the weight ratio between S and MO, we use the GDS globe discharge spectrometer to know to quantitative uh, measure the ratio between S and the MO is about 1 to 2. And then we can look at this TM image of the thickness of MOS2. It's about like 40 nanometer. And also we can see some right here, some nanopore. Okay, nanopore. And the EDEX shows that there's some SNMO signal located at deep AAO nanopore. So that means this MOS2 precursor, liquid precursor, are deeply penetrating into this nanopore. Okay, so you can see the signal right here. And we do this FIB, focus ion beam, to cut through the AO surface. Okay, we can see the depth of the AO. And we did the line scan, EDS line scan. We can see the S and MO signal. So that's the direct evidence to show that the MOS2 precursor deeply penetrating into the nanopore. And the depths can reach like 11 micron, more than 11 micron. And for the mechanical test, the anti-wearing test, we use the steel Viva head, and the diameter of each Viva fiber is about like 30 micron. 30 micron. And the Viva head diameter is about like 16 millimeter. And we apply the normal force. And this Viva head, we are moving, reciprocating at a constant speed. And we convert this constant speed into distance. So we can see the result shows the pure aluminum metal. Uh, it has the highest weight lost. And those MOS2 coating extremely enhance the weight loss. I mean, the weight loss reduced. You can compare with these two different samples. And we convert the previous data into wear rate. That's the weight loss divided by the original weight. So it's also the same result. You can see those coding samples has very low wear rate. And then we just modify the normal force and compare two different wearing distance. One is 720 and the other one is 1440. So if the wearing distance is 420 meters, uh, the normal force is independent. It's independent. That's mean if we just keep, you know, uh, wearing on the surface, the wear rate remain. The wear rate remain, and we just detect the debris of the steel Viva head by EDS, so we can see some signals on this debris, aluminum, MOS2, and iron, of course. And this shows the pictures of this coating before wear, and this picture shows the samples after wearing in 1,440 meters, so we can see the difference of the wearing area. Okay. And for the longer wearing distance, you can see the larger area. You can compare this aluminum alloy and the sample paralysis at 550. You can see the difference of the wearing area. And also we was working on the nano indentation, so you can see those samples with MOS2 coating and without MOS2 coating. So the indentation depths, the difference of the indentation depths, the sample without coating has the deeper depths. That's mean in low hardness, And also we just compare with the pure AAO anneal at different temperature, compare with the MOS2 coating paralyzed at 400, so we can see the difference. If we just to get the MOS2 coating sample paralyzed at 400 is right here, and the pure AAO paralyzed at 400 right here, so we can see the depth difference between them, right? Also, we can do the transit test. It's called DMA, dynamic mechanical test. So we can know the each depth whose mechanical property. For example, such like this, we can know the Young's modules. The Young's modules at different depths. For example, for this sample parallax at 550, this Young's modules is about like 95 GPa. 500 GPa. Also, work on the hardness in the MA dynamic mechanical test. So you can see for the sample polarized at 550, the highest hardness is located at the depths 500 nanometer. Okay, for deeper uh, sample hardness, the hardness is reduced. Okay, for the 500 samples, the highest hardness is located at the 450. After for that a deeper sample, the hardness reduced. Also, we just compare with the pure AAO anneal at 550 and MS2 coating AAO parallel at 550. So you can see the hardness as almost double, almost double. So my conclusion is that we can use the simple hot injection method to fabricate the MOS2 that can coat it at any porous metal with a very thin layer, with a thin layer. And after coating, the weight loss or the wear rate is dramatically reduced compared with the pure aluminum alloy and the MS2 coating alloy. The weight loss is a huge difference. Also, we do this line scanning. We know this MS2 precursor is deeply penetrating into this nanopore. And the MS2 coating is dramatically increased the hardness, surface hardness. Okay, almost double, almost double. Thank you for your attention. If you have any questions, please direct email me or just scan the QR code. You can reach me and ask any question that you want. Thank you.